So the next video that you will be able to see is the one that deals more specifically with the crude oil fractions that are derived from the fractional distillation of crude oil. Now, once again, at the bottom of the slide, as you can see, I've listed the MEDSEC assessment criteria. Okay, they are over here. And as you notice, they are basically the same criteria that you had for your first video. This is a circular learning pattern where you accumulate further knowledge with each video that you see. So basically we are reinforcing and we are increasing the knowledge that you would have learned from your first video. We are adding onto it. Now, basically, what you will learn from this video, and do pay close attention to each point that I have listed in this slide, you will learn these main points. First, there are various crude oil fractions that have very important uses in everyday life. We've said this, I will repeat it. Okay, crude oil can be refined, it can be broken down into refinery gases, into diesel, into petrol, into naphtha, etc., as you shall see. Each of these fractions has a list of very important functions in our everyday life. Okay, you should be able to understand that each fraction consists of hydrocarbons. As I said in the previous slide, okay, hydrocarbons are chemicals, okay, that consist only of two types of atom, hydrogen and carbon. And there is a very open, if you like, a very wide range of boiling points. The boiling points range from less than 40 degrees Celsius for the refinery gases. We call that the most volatile, the most easily evaporated gaseous fraction. And then we have the residual fraction, the heaviest fraction, the fraction that is tar-like. If you had to get a jug containing bitumen, and if you had to heat it up, even after heating it up, when you try to pour it, it's like pouring a very thick syrup. It's like a thick treacle, if you like, black. It's black and it flows very slowly. It's what is used in the mix that is used to surface our roads when you've got asphalting works taking place. You should be able to know that the shortest chain molecule fractions, so it's the refinery gas fractions, when we talk about the shortest molecules, we are talking about the refinery gases where the molecule chain length would be from C1 to C4. Okay, so the molecule chain length will dictate how far up the column the hydrocarbons will go. So the shortest chain molecules are the ones that will move furthest up the fractionating column, and the heaviest fractions are the ones that will stick to the bottom of the fractionating tower or column. When you see the video, you will be able to understand that the approximate chain length of fractions used in everyday life is very different. Okay, so from the next fraction, if we had to look, for example, at the fraction which is linked to petrol, the average chain length would be on average less than 10 carbon atoms. If you had to look at the average chain length for diesel, it would be at least around 15 carbon atoms plus. So you would be able also to link that to your observations in everyday life. I am sure that you would already have an idea at this stage that a diesel engine can be more polluting than a petrol engine when it comes to emissions of particulate black smoke emissions. Okay, it is harder to control such emissions if you have a diesel engine than when you have a petrol engine. The reason is, of course, if you have diesel with longer hydrocarbon chains, these are more difficult to break down completely into the combustion products that are carbon dioxide and water. We call those the complete combustion products than it is to break down petrol. Okay? Once you've seen the video, you will also be able to better appreciate that crude oil refining is not just linked to the production of the fuels that we use in everyday life, but it is also linked to the start of many chemical production processes, one of the most important being the manufacture of plastics. Now, I strongly suggest that you go through the video on the next slide. There is absolutely no commentary of my own. All you have to do is to press the play button, play through it the first time, return to the slide, replay my narration, or you might decide to just look through the learning outcomes I've listed in this slide, then go back to the video and replay it one more time. Make sure after you've done this twice that you can identify all of the learning outcomes on this slide from the 4-minute circa video clip that you are about to watch. Let's now move on to the video, and after that to my commentary on the slide after that.
In our other videos, we have learnt how fractional distillation is used to separate hydrocarbons into fractions with a similar boiling point. In this video, you will learn the names of some of the most important fractions and their uses. As you are now aware, large hydrocarbons have higher boiling points and so are removed at the bottom of the fractionating column. Smaller molecules condense higher up the column. We will now take a look at some of the common fractions as we move down from the top of the fractionating column. Some of the smallest molecules are between 1 and 4 carbons in length. This fraction has such a low boiling point that it is still a gas when it is removed from the very top of the fractionating column. This fraction is known as refinery gas or bottled gas. Bottled gas because it can be stored in bottles under high pressure. You could well have seen bottles of propane or butane running barbecues or heaters in your home, and these are examples of the refinery gas fraction. Petrol is between 5 to 7 carbons in length. It is still a fraction of small chain hydrocarbons, and therefore these vaporise at a low temperature and are easily ignited. This makes it useful as a fuel in the internal combustion engine of a car or other vehicles. Naphtha is not such a useful fuel, but it is a valuable source of organic molecules which can be cracked to make more fuels or form alkenes. Alkenes can be turned into polymers, and polymers can make plastics which are used in our everyday lives. Kerosene has an important use as a fuel for jet engines, in aircraft and even in some rockets. Kerosene is also called paraffin in some parts of the world and is a common fuel burnt in paraffin or kerosene lamps used for lighting. Diesel is the next fraction. It is a common fuel in cars, vans and lorries. It is not as volatile as petrol, and instead of spark ignition, it ignites under compression. Below diesel are the residue fractions. Fuel oil is a fuel used in power stations and ships. Lubricating oil, which sticks to surfaces and reduces friction and protects from rust. And finally, waxes, which along with the oils can be used for polishing surfaces. The very bottom fraction is bitumen. This is a thick black adhesive used on roads, either as the surface finish or combined with stone chippings to create a solid, resistant material. It can also be used to cover roofs due to its waterproofing properties. All these fractions are separated from the crude oil mixture. To try and explain the importance of crude oil, consider these facts. There are estimated to be over 1 billion cars in the world, of which many will be using petroleum as their fuel. There are many million flights each year, each burning kerosene fuel. Not forgetting the massive plastic that is made and used each day for products and their packaging. Even the bitumen used to surface and resurface roads around the world. As you can see, crude oil contains many useful products that just need to be separated from the crude oil mixture. Now, at the end of this lesson, you should have a better understanding of why crude oil is such a valuable resource and the use of each of the main fractions.
Now, by listening to my narration on this slide and also by watching the connected video on the next slide, you will be able to understand how immiscible mixtures. Now, what is an immiscible mixture? An immiscible mixture is a mixture of two liquids, okay, that cannot mix together, typically oil and water. We are going to focus in these two slides. Now in this slide and the diagrams that you've got below the text, and also in the next slide, which is a video of an English person doing a home demonstration on how to separate out vinegar, I believe it is, from sunflower oil. Okay, it's a vinaigrette. Okay, so it's he also does the separation using a blue colored dye. Okay, but I would like you to watch the video immediately after having understood the content of this lesson. It is directly related. Okay, so basically let's understand the difference between miscible and immiscible. Miscible is derived from mixing. So since substances can be mixed, they must be alike in chemical nature. Two miscible substances would be, for example, water and surgical spirit. You could try this very quickly if you like at home. Just take a small volume of water, take a small volume of surgical spirit, pour one into the other, and they do not form separate layers, they form a monolayer. So they are miscible, they mix together. You could do so if you like. Again, pour a small amount of, I don't know, wine, add it to water, even though the wine contains a certain alcohol content. Okay, of course, it will mix up very well with the water. Now, however, you would have noticed if you are trying to, for example, clean out a pan that has been used for frying and it still has a layer of oil, the only really way that you can clean it up is by adding soap, because soap can mix, so it's miscible with oil. However, if you try to just clean it out with water, the two substances are very different. Oil is hydrophobic, it is water hating, so it does not mix with water. They form separate layers and you will have a very hard time using a sponge, or perhaps even using a piece of iron wool to separate them out. By the time you have damaged your pan, it's much easier to use miscible soap than try just using water. Now, how could you actually separate oil and water from each other? There is a very important piece of glassware that you will find in any school laboratory. Now, I am referring to the separating funnel that you will see in the diagram, which is found at the bottom left. Okay, now I'm referring to this piece of equipment over here. Now what I'd like you to notice is that the shape over here, there is a large container volume, but at this point, right where I'm circling at the moment, this is a very, very narrow glass tube, meaning that it can only hold a very small volume of liquid. So it's a very ingenious solution. All you have to do is to add your mixture to the separating funnel, and as you might expect, of course, the oil floats on top of the water. Then all you do is, where I've circled, you will see that there is a tap. Okay, now you open the tap and carefully drain off the water at the bottom. Since the tube close to the tap, the part of the funnel close to the tap consists of a very narrow tube, you can remove a very small volume of water without removing any of the oil at the same time. By the time the oil level reaches the level of the tap, you just close off the tap. So if you like, the shape of the separation funnel is designed in such a way to allow a very fine separation, a very fine siphoning off of the water from the oil. You can very cleanly separate the water from the oil. The oil is left in the funnel, then all you have to do is to get a second beaker and drain off the oil content. In the video that you'll watch, the demonstrator actually uses 3 beakers. Why is this? The first beaker is used to collect the water, but he stops he closes the tap just before all of the water has been added. If you notice at the point where I've circled, when the tap is open, you will expect the oil to start coming down to the funnel. Okay, so the level of the oil will start to go down. It will start to move down the funnel. At the point where there is just very little water left to drain, there is the risk that if you keep on draining the water, some oil can be carried over. So for the last bit of water above the tap line, you don't keep on draining into the water beaker. You introduce a second beaker where you just drain off that very little volume where there is a risk of contaminating the water with the oil. Then a third beaker is used where the major part, where the biggest part of the oil volume can be drained. So in the first beaker you'll have pure water, in the third beaker you'll have pure oil, the middle beaker you can discard the contents. The second diagram that you see on the right is basically a further reinforcement of the diagram on the left. Once again, you can see the oil separating out and floating above the water. There is the separating funnel, a conical flask, and the stand. I've included the second diagram because the second diagram is what you would be expected to draw in the event of being asked to draw the diagram. Notice that diagrams in chemistry have to be clear. They have to clearly represent in outline, in a clean, solid outline, your equipment. The equipment must be proportionate in size. So the size of the conical flask must bear up well with the overall layout of the setup. Okay, so it mustn't be oversized. It must be of the correct proportion when you compare it to the burette stand, when you compare it to the separating funnel. Notice that there is no use of color. True that the solution, that the oil and the water, they have been shaded. Avoid shading. Okay, it is sufficient to just draw a separating line and label the top layer as oil and the bottom layer as water. Okay, now I strongly urge you to watch the video on the next slide. It is extremely well explained. You will see how, with the help of a separation funnel, you could actually experiment on your own at home and separate out oil from water. Okay, by the way, it is not expensive should you wish to buy it from a lab supplier. Okay, it would just cost a few euros. Okay, not too much money. Let's now move on to the next item in our presentation.